Hello everyone, I am Akiladi Charkupalli. I have chosen the topic Robomorphic Computing, a design methodology for domain-specific accelerators parameterized by robot morphology. So we have many complex robots such as manipulators, quadrupeds and humanoids. It can safely interact with the people in the dynamic unpredictable environments. So the robot morphology. So the morphology includes limbs, joints, and links. It's a part a chain of links, and then the joints that connect to those links. It has a quadruped robot might have four limbs with three links and a thigh, shin, and foot, for example. And then the design followed by a two-step procedure. Initially it creates a hardware template for the dynamics gradient, and then it set the template parameters to customize the accelerator. For an example, like a target robot model, it is an industrial manipulator. And then followed by the algorithm. Initially it computes the inverse dynamics, and then followed by the inverse dynamics gradient with respect to inputs from all the links, and finally it calculates the forward dynamic gradient by multiplication with the inverse of mass matrix. Robomorphic computing. It is a hardware design methodology for the robotics accelerators, in which they need high level information about a robot model to parameterize the features of the accelerator. And then it has two steps. It includes create hardware template. So for an algorithm, it is parameterized by key components of robot morphology, which includes limbs, links, and joints. So in these, by taking the parallelism from the loops over the robot's limbs and links, and then they're gonna map to the parallel processing elements into the hardware accelerator template. And then they're gonna also identify the linear algebra operations by the sparse robot matrices, and then they're gonna map with the functional units. And then we have the second step. It's set template parameters. So once the step 1 has done, that means hardware template has been created, it can be used to create the customized accelerators for many different robot models. And in these, they're going to use the number of limbs and links in the robot to set the number of parallel processing elements in the accelerator template. For example, they use the links in the manipulator which are connected to a joint, whose transformation matrix has only limited number of elements. And then with corresponding to the functional unit, they're gonna have the multiplication implemented by using a tree of multipliers and adders, and then it can be pruned by reducing the multipliers and adders. And then finally, when coming to the FGPA accelerator evaluation, it includes following steps. They need to compare the latency of a single execution of forward dynamics gradients for every processor CPU, GPU, and our FGPA implementation. And then they're going to check the joint transformation matrix sparsity for the FGPA. And then they need to check the accuracy and numerical precision also. By checking all of these together, they have a FGPA accelerator evaluation. From the picture we can see how robomorphic computing works. Initially it creates a parameterized hardware template, and then by following the template it sets the template parameters per each robot, let's say. And then in the algorithm they introduce inverse dynamics we're going to discuss. And then they for example in the robomorphology, it includes limbs topology and joint types. And then they're gonna do the problem by the accelerator hardware using accelerator hardware morphology, for example parallelism and the sparse linear algebra. So in robotics, the main processing pipeline is broken down into three fundamental stages. They are perception, mapping and localization, and motion planning and control. So these steps can be done in the sequential order. So during the perception, the initial state, a robot gathers information from the sensors and processes the data into usable semantic information, and then the robot uses that labeled data to construct a map with its surrounding environment and estimates its location in the map. And then finally, a robot plans and executes a safe obstacle-free motion trajectory through the space. We are seeing how robomorphic computing for the motion planning and control works. Initially, it creates a parameterized hardware template, and in these, first they implemented the robotic algorithm, and then they gone with the limb parallelism, and then it checked with the link parallelism, and then with the inertia matrix operations, and then it includes the joint transformation matrix operations, and then it also finally it includes with the subspace matrix operations. So when coming to the second step, by setting the template parameters per robot, so initially they set the limbs, for example let's say 5 limbs, and then for all the limbs they need to set the links. So there is a concurrency between the step 1 and step 2. They are interlinked with each other by performing the operations. So we can see like for the step 1 and step 2 we can see a coincidence for all the together. Like for the limbs they're gonna set the limbs, and then link they're gonna set the links, and then for the inertia matrix operations they need to set constant values. So it's a like a customized accelerator by involving all the step 1 and step 2 together. Now we have a look at the hardware system configurations for the project. Like it includes the platforms which are like the processor, cores and the max frequency, and we're going to compare with the CPU and GPU, its graphical processing unit, and FPGA, its field programmable gate array. And in the bottom picture we can see how FPGA coprocessor system implemented. So these algorithms can be addressed with robomorphic computing because they are tightly coupled with the physical properties of the target robot. And then the dynamics of soft robots with the flexible limbs can be like modeled as the piecewise approximation by using long chains of the rigid bodies. When we compare the picture, we have the left hind knee of the HYQ quadruped and then the right shoulder of the Atlas humanoid. Their transformation matrix has a sparsity pattern, and then by using robomorphic computing, those sparsity patterns directly program the structure of a sparse matrix vector multiplication units by pruning into a tree of multipliers and adders. And then we have like the examples over here in the picture by using the row 6 and row 5. So the algorithm, it includes 3 steps. In the initial step it computes inverse dynamics, and then it computes inverse dynamic gradient with respect to inputs from all lengths, and then finally it recovers the forward dynamics gradient by multiplication with the inverse of mass matrix as mentioned in the step 3. So in this paper the work they have done, like they have extended the software method into the world of hardware by using robomorphic computing, and the first ordered gradient of forward dynamics is a crucial kernel in many of the existing motion planning methods they have explained. And there is also a lot of motion planning techniques which include the software modern software implementations like rigid body dynamics and accompanying the gradient and making use of templating and the code generation to optimize functions for particular robot models. Like some of the related work is hardware design specifically for use in the robot acceleration, which may provide the significant benefits, and in the contrast between the combined actuator response rates and software solutions, it should be like it's considered as state of the art, and there is also a performance gap that is at least 1 order of magnitude wide in it. So for the experiment, this study has like several strengths. Like it is very instructive, and it involves people as participants, like social groupings, and the research is like a bit problem focused and context specific and future oriented too, and its aim is like to improve by participating all the contestants in it. So from the paper we got the findings like the authors offered a technique for converting robot morphology into a hardware accelerator morphology, and then when they compare CPU to the GPU, the execution of a single dynamic gradient calculation is speed up by 86 times using the FGPA accelerator. So in my opinion, the design process that is known as robomorphic computing is used for a variety of other important applications in robotics. Particularly, they mostly rely on robot morphology data. It includes like detection of collisions and localization, kinematics and dynamics. It's all for only like flexible robots that are referred to soft. So I plan to construct a template for those extra robotic applications which are not included, so they also need to use the same algorithm to implement it. Reference for the presentation. Thank you everyone.